Welcome, everyone. I'm excited to start our journey into understanding the structure of atom. Today's presentation is titled Structure of Atom, and we'll be exploring the fundamental building blocks of matter. We'll cover key concepts like atomic structure, subatomic particles, and how atoms form the basis of everything around us. Let's get started and discover the fascinating world of atoms together. Let's take a look at slide 2. Here, we see the contents of our presentation laid out clearly, starting from the very beginning with the discovery of the electron. From there, we move through key concepts like Rutherford's model of the atom, which was groundbreaking in its time, but also had its limitations. We then explore the electromagnetic spectrum and how electromagnetic radiation plays a crucial role in understanding atomic behavior. Next, we delve into the wave nature of light, which introduces a fundamental duality. Light behaves both as a wave and as a particle. This duality leads us to Planck's quantum theory, a pivotal concept that revolutionized physics. We examine the particulate nature of light through experiments like the photoelectric effect, further illustrating how light can behave like particles. As we progress, we explore the results of important experiments and the implications they have for our understanding of atomic and subatomic particles. This sets the stage for more advanced ideas like quantum numbers, electron spin, and the quantum mechanical model of the atom, which form the core of modern atomic theory. Throughout, we're connecting these ideas to build a comprehensive picture of atomic structure and behavior, leading us toward the more detailed topics covered in subsequent slides. Let's take a closer look at how we confirmed the flow of current in a cathode ray tube. To do this, we made a small hole in the anode and coated the back of the tube with a phosphorescent material called zinc sulfide. When the cathode rays hit this coating, a bright spot appears, helping us visualize the path of the rays. A cathode ray tube itself is made of glass and contains two thin metal pieces called electrodes, sealed inside. When we apply a high voltage across these electrodes in a low-pressure gas environment, an electrical discharge occurs, which we can observe only under these specific conditions. We can also control the pressure of different gases inside the tube by evacuating air, making it possible to study how gases behave under these conditions. Once the voltage is high enough, a stream of particles begins moving from the negative electrode, the cathode, toward the positive electrode, the anode. These particles are what we call cathode rays or cathode ray particles. This experiment was crucial because it led to the discovery of the electron. It showed us that these rays are actually streams of tiny charged particles, electrons, moving through the tube. So, in essence, this slide highlights how the flow of current was visually confirmed, and how this process ultimately led to understanding the existence of the electron, a fundamental breakthrough in atomic science. The characteristics of cathode rays are quite fascinating because they don't depend on the type of material used for the electrodes or the kind of gas inside the tube. This tells us that these rays behave consistently, regardless of the specific materials involved. When we introduce electrical or magnetic fields, the behavior of cathode rays gives us a crucial clue. They behave as if they are negatively charged particles. This observation strongly suggests that the rays are actually made up of tiny particles called electrons. In a situation where there's no electrical or magnetic field applied, these rays travel in straight lines. This straight line motion is important because it shows that in the absence of external forces, the rays move predictably. Now, these rays themselves are invisible to our eyes, which might seem like a limitation. However, we can observe their behavior by using fluorescent or phosphorescent materials, special materials that glow when struck by these rays. This glowing effect allows us to see where the rays are going and how they behave. Finally, it's interesting to note that the cathode rays originate from the cathode and move toward the anode. This directionality helps us understand the flow of these particles within the tube and plays a key role in our overall understanding of atomic structure and electrical conduction. The deflection of electrons from their original path increases as we increase the voltage across the electrodes or strengthen the magnetic field. Essentially, stronger electrical or magnetic fields cause greater deviation of the electrons. Now, the size of this deflection also depends on the particle's mass. The lighter the particle, the greater the deflection, and vice versa. Another key point is the charge-to-mass ratio, which is approximately 1.7588 times 10 to the power of 11 coulombs per kilogram. This ratio helps us understand how the electrons respond to electric and magnetic fields. When electrons deviate from their straight path, applying both electrical and magnetic fields can help bring them back to their original trajectory, allowing them to hit the screen at a specific point, which we call point B. If we apply only a magnetic field, electrons will strike the cathode ray tube at a different point C conversely. If only an electric field is applied, electrons deviate and hit at point A. This shows that the greater the charge on the particle, the stronger its interaction with the fields, leading to greater deflection. And finally, the amount of deviation depends on the ratio of the charge to the mass of the electron, which we determine using a cathode ray tube setup with perpendicular electric and magnetic fields. This experiment helps us understand the fundamental properties of electrons and their behavior under electromagnetic forces. The behavior of these particles in magnetic or electrical fields is opposite to that observed for electrons or cathode rays. This means that they are attracted or repelled in the opposite direction, which indicates they carry a positive charge. Interestingly, the charge-to-mass ratio of these particles depends on the gas from which they originate, highlighting that their properties can vary based on their source. Now, moving on to the discovery of neutrons, Chadwick hypothesized that when alpha particles bombarded a thin sheet of beryllium, they emitted electrically neutral particles that had a slightly greater mass than protons. He named these particles neutrons. This was a groundbreaking discovery in the history of chemistry because it explained the existence of additional nuclear particles that couldn't be accounted for before. Next, we see that the smallest and lightest positive ion was obtained from hydrogen, and this particle is called the proton. Protons are fundamental because they carry a positive charge and are a core component of atomic nuclei. Some positively charged particles actually carry a multiple of the fundamental unit of electrical charge. This means that not all positive ions are simply single protons. Some are multiples, which affects how they behave in fields. Unlike cathode rays, these positively charged particles depend on the nature of the gas present in the cathode ray tube. These gases form simple positively charged ions, and their properties change depending on the gas involved. Lastly, the characteristics of these rays, known as canal rays, were discovered through electrical discharge experiments in a modified cathode ray tube. This led to the identification of particles carrying positive charge, further expanding our understanding of atomic structure and the particles involved. According to Thomson, the atom was thought to be spherical in shape. It had positive charged particles and negative charged particles that were equally distributed throughout, which meant the atom was electrically neutral. This idea was quite revolutionary at the time because it suggested that atoms had an internal structure. Sometimes, this model is called the plum pudding model because it resembles a pudding with embedded fruit, or even a watermelon with the seeds spread inside. Understanding this model helps us see how early scientists visualized the atom and set the stage for more advanced discoveries later on. It's a key step in our overall journey to understand atomic structure. Let's look at what Rutherford observed during his experiment. A very small number of alpha particles, about 1 in 20,000, actually bounced straight back, nearly reversing direction with a deflection of nearly 180 degrees. This was quite surprising and indicated something significant about the atom's structure. A small fraction of alpha particles were deflected by small angles, which suggested that there was some repulsive force at play, but not everywhere in the atom. The key idea here is that this deflection had to be caused by an enormous repulsive force, which revealed the presence of a positive charge within the atom. This positive charge must be concentrated in a very tiny region because it was able to repel and deflect the positively charged alpha particles. Most of the space inside the atom, however, was empty, as evidenced by the fact that most alpha particles passed straight through the gold foil without any deflection. Only a few were deflected, indicating the presence of concentrated positive charge in a small area. Now, to connect this to the experiment's observations, most alpha particles went through the foil without any change in their path, which was quite unexpected at the time. Rutherford directed a high-energy stream of alpha particles at a thin gold foil, which was surrounded by a fluorescent zinc sulfide screen. When alpha particles struck the screen, tiny flashes of light appeared at the impact points, allowing us to see the scattering. This experiment became famous as Rutherford's alpha particle scattering experiment. It fundamentally changed our understanding of the atom and led to the development of the nuclear model, where the atom has a tiny, dense, positively charged nucleus at its center. Now, let's talk about how electrons and the nucleus stay together. They are held together by electrostatic forces of attraction, which are pretty strong and keep these particles bound within the atom. In the early models, the nucleus was thought to be surrounded by electrons moving at very high speeds. These electrons traveled in circular paths called orbits, kind of like planets around the sun. Most of the atom's positive charge, along with the majority of its mass, was concentrated in this tiny, dense region we call the nucleus. This small but incredibly important part of the atom is central to understanding atomic structure. So, in summary, the nucleus is where the positive charge and most of the mass are packed tightly together, and electrons move around it in these high-speed orbits, all held in place by electrostatic attraction. This concept helps us grasp how atoms are structured and the forces that keep them stable, which is fundamental to our overall understanding of matter. Now, let's look at some key concepts related to atomic structure. The mass number, represented by A, tells us the total number of protons and neutrons in an atom's nucleus. Think of it as the total weight of the nucleus, which is crucial for identifying isotopes. The number of protons, Z, defines the atomic number, and it's also equal to the number of electrons in a neutral atom, maintaining electrical neutrality. The neutrons, represented by N, don't affect the charge but contribute to the mass. When we talk about protons and electrons together, we call them nucleons. This term emphasizes their fundamental role in the nucleus and the atom's overall structure. Understanding the atomic number and mass number helps us distinguish different elements and isotopes, and it ties into the larger theme of understanding atomic identity and stability in matter. Now, let's talk about the chemical properties of atoms. These properties are mainly controlled by the number of protons in the nucleus. Because of this, atoms of the same element tend to have similar chemical properties and behave in similar ways during chemical reactions. Next, let's look at hydrogen, which has 3 isotopes: protium, deuterium, and tritium. Isotopes are atoms of the same element. They have the same atomic number, but they differ in their mass number. That means they have different numbers of neutrons. On the other hand, we have isobars. These are elements that have the same mass number but different atomic numbers. So, they are different elements, but their total number of protons and neutrons adds up to the same total mass. Understanding the differences between isotopes and isobars is crucial because it helps us grasp how elements can vary and how their properties are influenced by nuclear structure. This concept ties into the broader theme of atomic structure and how it affects chemical behavior. So, when we look at Rutherford's model of the atom, we see some clear limitations. For starters, it simply couldn't explain quantum mechanics as a whole. Quantum mechanics is fundamental to understanding atomic and subatomic behavior, but Rutherford's model doesn't account for the strange, probabilistic nature of particles at that scale. It also couldn't explain planetary motion under the influence of gravity. While it gave us a good picture of the nucleus and electrons, it didn't address how electrons orbit or why they don't spiral into the nucleus over time, which is a key question in physics. Additionally, Rutherford's model couldn't explain Maxwell's electromagnetic radiation properties. Maxwell's equations describe how electromagnetic waves behave, but Rutherford's model didn't incorporate the wave nature of light or how atoms emit or absorb radiation. And finally, it couldn't explain the gravitational force in nature. Gravity is a fundamental force, but Rutherford's atomic model mainly focused on electrostatic forces within the atom, leaving gravity's role at the atomic level unexplored. Overall, these shortcomings highlight why Rutherford's model, while groundbreaking for its time, was just a stepping stone toward a more complete understanding of atomic structure. Now let's take a closer look at electromagnetic radiation. There are two key components to it, an electric field and a magnetic field. These two fields work together and are perpendicular to each other, forming what we call a wave. This wave travels through space, carrying energy from one point to another. Electromagnetic radiation isn't just one thing. It includes a wide range of waves like radio waves, microwaves, and X-rays. Each of these has different properties and uses, but they all share this fundamental wave nature. When we look at the electromagnetic spectrum, visible light is just a small portion of it. It's the part that our eyes can detect, which is why we see colors. Most of the spectrum, however, is invisible to us, like radio waves or X-rays. Understanding this spectrum helps us appreciate how various forms of electromagnetic radiation play essential roles in our daily lives, from communication to medical imaging, all connected by the wave nature we just discussed. Now let's take a closer look at some fundamental wave properties. First, frequency, represented by the Greek letter nu, is the number of wave cycles that pass a specific point each second. We usually measure this in hertz, or Hz. Think of it as how many times the wave rises and falls every second. Next, we have amplitude, which is essentially the size or the height of the wave. If you imagine a wave on the ocean, the amplitude is how tall the wave is from its resting position to its crest. This relates to the energy carried by the wave. The higher the amplitude, the more energy it has. Then there's wavelength, represented by the Greek letter lambda. Wavelength is the distance between two corresponding points on successive waves, say, from crest to crest or trough to trough. It gives us a sense of how stretched out or compressed the wave is. Connecting all these points to our overall theme, understanding these wave properties helps us grasp the wave nature of light. Light behaves like a wave in many ways, and these concepts are key to explaining phenomena like diffraction, interference, and even how different colors of light are related to wavelength. So, by mastering frequency, amplitude, and wavelength, we're better equipped to understand the true nature of light. Let's take a closer look at why classical physics couldn't fully explain blackbody radiation. As it turns out, classical theories failed to account for the observed spectrum, especially at higher energies. One key point is that as the temperature increases, the peak wavelength, which we denote as lambda, shifts to shorter values. This means the maximum energy, or E, also becomes higher. So higher temperatures lead to a shift towards shorter wavelengths and higher energies. This behavior was puzzling under classical physics, which couldn't explain why energy distribution behaved this way. That's where Planck's quantum theory comes in. It introduced the idea that energy is quantized, meaning it comes in discrete packets, or quanta. This was a groundbreaking shift because it explained the observed blackbody spectrum accurately, especially at higher energies and shorter wavelengths. So, essentially, Planck's theory bridged the gap that classical physics couldn't, allowing us to understand phenomena like blackbody radiation in a more complete way. Let's take a closer look at Planck's equation. It reveals some fascinating ideas about light. First, it shows that light has a particle character, meaning that under certain circumstances, light behaves like tiny particles called quanta. This was a groundbreaking concept because it challenged the traditional wave view of light. Secondly, it tells us that energy is quantized. In other words, energy isn't continuous but comes in discrete packets. This idea was revolutionary and laid the foundation for quantum theory. Now, going back to 1900, Max Planck was studying black body radiation. He was trying to understand the spectrum of energy emitted by objects that absorb all radiation that hits them. To explain the shape of this energy spectrum, he realized he had to make a bold assumption: that electromagnetic radiation, which includes visible light, is made up of these tiny energy packets. This was a key step in understanding the quantum nature of energy and light. Let's talk about the relationship between frequency and wavelength. Frequency is inversely proportional to wavelength, which means that as one increases, the other decreases. Think of it this way: a shorter wavelength corresponds to a higher frequency, and a longer wavelength corresponds to a lower frequency. Now, all of this ties into the speed of light, which is the product of the frequency and the wavelength. The constant value for this speed is approximately 3x10 to the 8th meters per second. This is a fundamental point because it shows that no matter the type of light, in a vacuum, it always travels at the same speed. The velocity of light is, in fact, the fourth key variable we consider when studying light. So, understanding these relationships helps us see the wave nature of light and how its properties are interconnected. Visible light is actually just a small part of the entire electromagnetic spectrum. When we think about electromagnetic radiation, it's useful to categorize it based on either wavelength or frequency. This helps us understand the different types of radiation and their properties. Now, when we talk about the wave nature of light, we're delving into how light behaves like a wave, which is key to understanding many phenomena, from diffraction to interference. Recognizing that light has wave properties connects directly to our broader theme of understanding how light interacts with matter and the universe. So, in essence, the wave nature of light is fundamental to grasping its behavior across the spectrum. When electrons gain more energy, they move faster, which means they have higher kinetic energy when they leave the metal. If they receive enough energy, these electrons can actually break free from the metal's surface. This process happens because the energy from the light is transferred directly to the electrons inside the metal. So, when light hits a metal surface, it can generate what we call photoelectrons, electrons that are ejected from the metal due to this energy transfer. This entire phenomenon is known as the photoelectric effect, and it really highlights the particulate, or particle-like, nature of light. It's a key concept because it shows that light isn't just a wave, but also has particle properties. This understanding helps us see how energy transfer at the microscopic level works, connecting the behavior of light and electrons in a very fundamental way. Now let's look at how current flow is used to monitor light intensity. When light hits the device, electrons are collected at the anode, creating a measurable current. This current directly relates to the number of photons striking the surface, so it gives us a way to gauge how bright the light is. Next, consider how light interacts with the cathode. Light of a certain frequency, which we call nu, strikes the cathode. If this frequency exceeds a specific threshold value, nu0, electrons are ejected from the surface. This threshold frequency is crucial because it explains why not all light causes emission. Only light with enough energy or frequency can do so. This entire process is what we refer to as the photoelectric effect. It's the basis for how photocathodes work, converting light directly into an electrical signal. Understanding this effect helps us see the particle nature of light, how photons, which are particles, can transfer enough energy to eject electrons. This concept is fundamental in many modern technologies, from cameras to scientific instruments. Alright, so we know that the speed of light, c, is equal to the frequency, nu, times the wavelength, lambda. That means, if we rearrange the formula, the frequency is c divided by lambda. Now, this is a key concept because it links the wave's speed, which is constant, to its wavelength and frequency. In this example, we're looking at neon lights that emit a beautiful orange-red glow. The wavelength of this light is given as 670 nanometers. Our goal is to find its frequency. Remember, since c is the speed of light, which is approximately 3 times 10 to the 8th meters per second, we need to make sure our units are consistent. So, we'll convert 670 nanometers into meters, which is 670 times 10 to the minus 9th meters. Once we have that, we simply divide the speed of light by this wavelength, and that will give us the frequency of the light in hertz. This calculation helps us understand the relationship between the wavelength of light and its energy, which is a fundamental concept in wave physics. Neither waves nor particles provide an entirely accurate description of all the properties of light. Instead, we use the model that best explains the specific properties we're examining. For example, particles of light are called photons, and light is best described as a particle when it's imparting energy to another object. This is especially clear in phenomena like the photoelectric effect, which cannot be explained by a wave model, but makes perfect sense when we think of light as particles. This idea of wave-particle duality means that depending on the situation, light can be described as a wave or as a particle. So, understanding this duality helps us better grasp the complex nature of light and its behavior in different contexts. Let's take a closer look at some key points from our photoelectric experiments. First, you'll notice that the kinetic energy of the emitted electrons is actually independent of light intensity. This means that no matter how bright the light is, it doesn't affect how much energy each electron carries away. As we increase the frequency of the light, the kinetic energy of the emitted electrons increases linearly. So, higher frequency light results in electrons with greater kinetic energy, which is an important observation that supports the idea that energy is quantized. Now, when we talk about light intensity, increasing it causes more photoelectrons to be emitted. That is, the number of electrons increases with brightness. However, there's a crucial point here. The value of the threshold frequency, often called nu-zero, depends on the metal used. Different materials have different work functions, so this threshold varies. Finally, for frequencies greater than this threshold, nu-zero, the number of electrons emitted becomes independent of the frequency. Instead, it's primarily influenced by the intensity of the light. All of these points help us understand the fundamental nature of the photoelectric effect and set the stage for the quantum explanation of light. Now let's talk about Planck's constant, which is denoted as h and has a value of 6.626 times 10 to the power of minus 34 joule-seconds. This constant is fundamental in quantum mechanics because it relates to the energy of a photon. Specifically, the energy of a photon, E, is directly proportional to its frequency, nu. That means, as the frequency increases, the energy of the photon increases as well. On the other hand, the energy is inversely proportional to the wavelength, lambda. So, shorter wavelengths correspond to higher energies, and longer wavelengths correspond to lower energies. This relationship highlights the particle-like nature of light, which is a key point in understanding phenomena like the photoelectric effect. Overall, these concepts help us see how light isn't just a wave, but also exhibits particulate properties, linking directly to the broader theme of the particulate nature of light we've been exploring. This slide explains the photoelectric effect, which is a key piece of evidence for the particulate nature of light. Essentially, the energy of a photon, represented as E photon, is split into two parts: the binding energy, which is the energy holding an electron to the metal, and the kinetic energy, which is the energy the electron has once it's emitted. When the frequency of the incoming light is above a certain threshold frequency, denoted as nu-zero, the photon has enough energy to overcome the binding energy and still have some leftover energy to give the electron as kinetic energy. That's why we see electrons being emitted with some velocity. However, if the frequency of the light is below this threshold frequency, no electrons are emitted at all because the photon doesn't carry enough energy to free the electron from the metal. The threshold frequency, nu-zero, is basically the minimum frequency of light needed to eject an electron, and the binding energy is the energy required to hold that electron tightly to the metal. This concept is fundamental because it shows that light behaves as particles, or quanta, with specific energies, rather than just a continuous wave. It's a crucial step in understanding the particle nature of light and how energy is transferred at the quantum level. Now, on this slide, we're looking at a typical laser in a standard laser printer, which emits light at a wavelength of 780 nanometers. This is a very specific wavelength, and understanding its energy is crucial for appreciating how lasers work at a fundamental level. The key question here is, what is the energy of a single photon of this light? Remember, in the context of electromagnetic radiation, each photon carries a specific amount of energy directly related to its wavelength. This is important because the energy of the photon influences how the laser interacts with materials, like the toner and paper in our printer. To find this energy, we'll use the fundamental relationship between energy and wavelength, which involves Planck's constant and the speed of light. As we go through this example, keep in mind that understanding photon energy helps us grasp how lasers precisely target and manipulate materials, which ties into the broader themes of light-matter interaction and the applications of quantum mechanics. Now, let's explore how light behaves when it interacts with different materials. First, light separates into its component colors, which is something we see clearly in a rainbow or when light passes through a prism. This happens because different colors, or wavelengths, of light bend at different angles. In fact, light bends at an angle depending on its wavelength, which is a key concept in understanding refraction. When light moves from one medium to another, say, from air into water, its speed changes. This change in speed causes the light to bend, a phenomenon we call refraction. So, to summarize, refraction is all about the bending of light as it transitions between media of different densities, and this bending depends on the wavelength of the light. This is a fundamental aspect of the wave nature of light and helps us understand many optical effects around us. Let's look at this interesting photoelectric experiment. We have ultraviolet light shining on potassium metal with a wavelength of 337 nanometers. Now, when this light hits the surface, it ejects electrons, and we measure their kinetic energy, which in this case is 2.3 times 10 to the minus 19 joules. The key question here is, what is the electron binding energy for potassium? Remember, the binding energy is essentially the energy needed to free an electron from the metal. So, what we need to do is relate the energy of the incident photons to the kinetic energy of the emitted electrons and the binding energy. First, we calculate the energy of the photon using the equation E equals hc over lambda. Here, h is Planck's constant, c is the speed of light, and lambda is our wavelength, 337 nanometers. Once we have the photon energy, we subtract the measured kinetic energy of the electrons to find the binding energy. This approach highlights how the photoelectric effect allows us to determine atomic and electronic properties, like the binding energy, based on measurable quantities. And remember, this is a great example of how quantum concepts directly connect to experimental data, helping us understand the structure of atoms. When light is emitted, the atom transitions from a higher energy state to a lower one, releasing energy in the form of light. Atoms can only exist in a limited number of these energy states, and each state has very specific energy levels. This means that the wavelengths of light they emit or absorb aren't random. They are unique to each element. In fact, these wavelengths are well separated or discrete, which makes them like a fingerprint for each element. This pattern of specific wavelengths absorbed and emitted by an element is called its atomic spectrum. Recognizing these spectra helps us identify elements and understand their behavior in different environments. Electrical current dissociates molecular H2 into excited atoms, which then emit light at specific wavelengths. This process is fascinating because it shows how energy input, in this case electrical energy, can break molecular bonds and excite individual atoms. When these excited atoms return to a lower energy state, they release that energy as light. Interestingly, for molecular hydrogen, this emission occurs at 4 distinct wavelengths, giving us a spectrum of lines. These lines are like a fingerprint, revealing the unique energy transitions within the atoms. Connecting this to our overall theme, understanding these spectra helps us interpret the physical conditions of astronomical objects and laboratory plasmas alike. It's a perfect example of how atomic behavior under energy excitation can tell us so much about the universe around us. Now, this can be demonstrated in various ways, like in the lab, with stars, or even fireworks. The key idea here is that we can use spectra to identify elements. And what's fascinating is that each element has a unique spectrum, kind of like a fingerprint. This uniqueness allows us to determine what elements are present just by analyzing their spectral lines. So, understanding atomic spectra is essential because it helps us connect the tiny details we observe in spectra to the larger picture of the atomic structure, which is a core part of understanding the Bohr model and how atoms behave. All right, let's break down this problem. When a hydrogen atom transitions from the energy level E3 to E1, it emits a photon with a wavelength of 102.6 nanometers. Similarly, if it transitions from E3 to E2, the emitted photon has a wavelength of 656.3 nanometers. Our goal here is to find the wavelength of the light emitted when the atom makes a transition from E2 to E1. Essentially, we're looking at the difference in energy between these two levels and figuring out the corresponding wavelength. Remember, the energy of a photon is related to its wavelength by the equation E equals hc over lambda, where h is Planck's constant, c is the speed of light, and lambda is the wavelength. Since we know the wavelengths for the transitions from E3 to E1 and E3 to A2, we can relate these to the energy differences between the levels. The key point is that the energy difference between E3 and E1 equals the sum of the differences from E3 to E2 and E2 to E1. So, by calculating the energies corresponding to those wavelengths, we can find the energy difference for E2 to E1, and then convert that back into a wavelength. Remember, the energy difference is proportional to 1 over the wavelength. So once we find the energy difference for E2 to E1, we can find the wavelength by taking the reciprocal of that energy difference, multiplied by hc. This approach ties into the overall theme of understanding atomic transitions and how energy levels relate to the photons emitted, which is fundamental in spectroscopy and quantum mechanics. Let's do the calculations, step by step, to find that wavelength. Let's explore how electrons behave around the nucleus. Lower energy orbits are closer to the nucleus because of electrostatics, the attractive force between the positively charged nucleus and the negatively charged electrons. This means electrons tend to settle in these lower energy states, which are more stable. When electrons move from higher to lower energy orbits, they emit energy, often in the form of light or photons. Conversely, if an electron absorbs energy, say from heat or light, it can jump from a lower to a higher energy orbit. Now, although electrons don't actually orbit the nucleus in perfect circles like planets around the sun, this model helps us understand key phenomena like absorption and emission of light. It's a simplified way to visualize how electrons behave in atoms, and it's fundamental to our understanding of atomic structure. This is the basis of the Bohr model, which, while not perfect, provides a useful framework for explaining these energy transitions. When atoms return to their ground state, they do so by releasing energy in the form of light. This process is fundamental because it explains how atoms emit specific colors or wavelengths of light. Now, when an atom absorbs energy, its electrons don't just sit still. They jump to a higher energy level, and this is what we call the excited state. Think of it as the electrons getting a boost or a lift to a higher orbital. But this state isn't stable. The electrons tend to want to go back to their original lower energy level, which is known as the ground state. When they do, they emit that excess energy as light, which is what we often observe in phenomena like fireworks or neon signs. Understanding this cycle, the electrons moving to excited states and then returning to the ground state by emitting light, is key to grasping the behavior of atoms and the foundation of the Bohr model of the atom. The Rydberg equation is an empirical formula, which means it was derived from experimental data rather than from first principles. It specifically relates the wavelengths of the lines we observe in the hydrogen spectrum. Essentially, it helps us understand the pattern and spacing of these spectral lines. The equation takes into account the different energy transitions within the hydrogen atom, allowing us to predict the exact wavelengths of the emitted or absorbed light. This connection between the spectral lines and the atomic structure is a key step in understanding atomic spectra and supports the broader concept of how electrons behave within atoms. So, while the equation itself might seem simple, it really opened the door to deeper insights about atomic energy levels and spectral behavior. Let's look at an example now, example 4.8, where we determine the wavelength of light emitted when a hydrogen atom's energy level drops from n equals 4 to n equals 2. This is a classic case that showcases how changes in energy levels correspond to specific wavelengths of light. Remember, in the Bohr model, when the atom transitions between these levels, energy is released in the form of light. The key here is to understand how to calculate that wavelength using the energy difference. We'll use the Rydberg formula, which relates the wavelengths to the initial and final energy levels. This example helps us connect the quantized energy levels to observable spectral lines, reinforcing the idea that atomic spectra are discrete and predictable. It's a practical illustration of how atomic structure influences the light we see, tying back to the overall theme of atomic spectra and the Bohr model. As the orbital radius increases, so does the energy associated with that orbit. This means that electrons in orbits farther from the nucleus have higher energy levels. An atom has a specific set of these energy levels, or orbits, which are both definite and discrete. Electrons can occupy these levels without emitting or absorbing electromagnetic radiation, unless they transition between levels. Now, let's talk about the key ideas behind Bohr's theory. In 1913, Niels Bohr took Planck's quantum theory and applied it to explain the hydrogen spectrum. This was a major breakthrough because it helped us understand how atoms emit specific wavelengths of light. Essentially, Bohr proposed that electrons orbit the nucleus in certain allowed paths or energy levels, and they only absorb or emit energy when they jump between these levels. So the main takeaway here is that the energy of an electron depends on its orbit, and as it moves to higher orbits further from the nucleus, its energy increases. This concept forms a fundamental part of how we understand atomic structure and spectral lines today. Let's take a closer look at the key variables involved in describing an electron's motion in an atom. We have v, which represents the velocity of the electron, m for its mass, and r for the radius of its orbit. These are fundamental in understanding its dynamics. Then there's h, Planck's constant, a critical number in quantum mechanics, and n, which stands for the energy levels the electron can occupy, starting from 1 and going upwards. 2, 3, 4, and so on. One of the most important concepts here is the angular momentum of the electron. We express it as mvr, which equals nh over 2 pi. This equation tells us that the angular momentum isn't just any value, it's quantized, meaning the electron can only have specific, discrete angular momentum values. Now, regarding the electron's movement, it travels in a circular orbit around the nucleus. Its motion follows the usual laws of mechanics and electrostatics, but with a crucial twist. Its angular momentum is restricted to these particular quantized values. This restriction is what leads to the stability of certain orbits and the discrete energy levels we observe in atomic spectra. Now let's look at the origin of absorption spectra. When light with a specific wavelength and frequency hits an atom, electrons can absorb that energy and jump from a lower energy level, like the n equals 2 orbit, to a higher one, such as n equals 4. This process creates the absorption spectrum, which appears as dark lines or bands against a continuous background. On the other hand, the emission spectra arise from a different process. When electrons drop from a higher energy level, like n equals 4, down to a lower one, such as n equals 1, they release that energy as light of a characteristic wavelength and frequency. This results in bright lines or bands in the emission spectrum. These concepts are fundamental because they show us how atoms interact with light, and they help explain why each element produces a unique spectral fingerprint. This understanding ties into the bigger picture of atomic structure and how energy levels govern atomic behavior. the theory fails for all other elements because it is not an adequate theory. While Bohr's model accurately explains the hydrogen emission spectrum, it doesn't hold up when we look at more complex atoms. This highlights that although Bohr's model was a significant step forward, it has its limitations. It's important to recognize that a theory must be comprehensive and applicable to various cases to be truly effective. So, in the broader context of atomic models, Bohr's theory is a good starting point, but it's not the final answer for understanding all atomic spectra. Now, let's talk about how the electron wavelengths are described by the de Broglie relationship. This is a key concept because it links the wave and particle nature of electrons. A crucial element of Louis de Broglie's dissertation was the idea that electrons don't just behave like particles, they also exhibit wave-like properties. In 1925, de Broglie published his PhD dissertation, where he proposed this groundbreaking idea. Essentially, he suggested that electrons, which we usually think of as particles, also have wave characteristics, and their wavelengths can be calculated using the de Broglie equation. This was a major step in understanding quantum behavior and helped bridge the gap between classical and quantum physics. So, in summary, the wave nature of the electron is fundamental to modern quantum theory, and de Broglie's work was instrumental in establishing this concept. Let's walk through an example to find the wavelength of an electron. Suppose we have an electron with a mass of 9.11 times 10 to the minus 31 kilograms, and it's moving at a velocity of 5.65 times 10 to the 7 meters per second. Remember, Planck's constant is 6.626 times 10 to the minus 34 joule seconds, which is also equal to 6.626 times 10 to the minus 34 kilogram meter squared per second. The key idea here is that, according to quantum mechanics, particles like electrons exhibit wave-like properties, and their wavelength can be calculated using de Broglie's equation. This equation relates the wavelength to the momentum of the particle, which is its mass times velocity. So, to determine the wavelength, we first calculate the momentum by multiplying the mass by the velocity. Then, we divide Planck's constant by this momentum to find the wavelength. This example underscores the wave nature of electrons, showing that even tiny particles have wave characteristics that we can quantify. It's a fundamental concept that bridges classical and quantum physics and helps us better understand the behavior of matter at microscopic scales. Electron microscopes use this fascinating phenomenon to achieve such incredible magnification. When detecting an electron, we need to use electromagnetic radiation, which actually displaces the electron itself. This is a crucial point because it highlights a fundamental limit in how precisely we can measure small particles. In fact, it's impossible to determine both the position and momentum of an electron at the same time with perfect accuracy. This idea was formalized by Werner Heisenberg in 1927 and is known as the uncertainty principle. It really underscores the strange and counterintuitive nature of quantum mechanics, where the very act of observing affects what we can know about a particle. This concept is central to understanding the quantum mechanical picture of the atom and helps explain why particles behave so differently at such tiny scales. The energy of the orbitals is quantized, just like in the Bohr model. This means electrons can only occupy specific energy levels rather than any arbitrary energy. The quantum mechanical model, however, takes this a step further by describing electrons as waves that are spread out through a region of space, which we call an orbital. Unlike the Bohr model, where electrons are depicted as particles moving in fixed circular orbits, the quantum mechanical model shows that electrons are delocalized, existing as a cloud of probability within an orbital. This shift from fixed orbits to wave-like behavior was a major development that replaced the earlier Bohr model, giving us a more accurate and comprehensive understanding of atomic structure. Let's take a closer look at how wave behavior is described in quantum mechanics. Here, H represents the operator, which acts on the wave function. E is the energy associated with the system, and Backslash stands for the wave function itself. The wave function is key because it encodes all the information about the quantum state of a particle. The Schrödinger equation then relates these components and provides a way to predict how the wave function evolves over time. Now, an important point to highlight is that electrons, which we often think of as particles, actually exhibit wave-like behavior. This was a groundbreaking realization back in 1927 when electron diffraction was first observed. The diffraction of electrons demonstrated that they don't just behave like tiny bulked balls, but also display properties characteristic of waves, such as interference and diffraction. Connecting this to our broader discussion, this wave-like nature of electrons is fundamental to understanding the quantum mechanical model of the atom. It helps us explain many phenomena that classical physics couldn't, giving us a more complete picture of atomic and subatomic behavior. Now let's talk about the index, which we denote as N. This index is used to label the different solutions of the wave function. It's important to understand that for any given potential interaction, there are multiple solutions or solution sets that describe how the electron behaves. Moving on, the probability density is a crucial concept. It tells us the likelihood of finding an electron in a particular region around the nucleus. Essentially, it highlights where the electrons are most likely to be located, helping us visualize their probable positions. When we solve the Schrödinger equation, we don't just get one number, but three sets of numbers called quantum numbers. These quantum numbers are vital because they give us detailed information about the electron's location in space, including the three-dimensional orientation of the orbital. They help us understand the shape, size, and orientation of the regions where the electron is most likely to be found. Now, shifting focus to potential energy, which plays a more significant role in describing atomic structure. This potential energy arises from the Coulombic attraction between the positively charged nucleus and the negatively charged electrons. The stronger this attraction, the more tightly bound the electrons are. Finally, we need to remember that the total energy of an electron isn't just potential energy. It also includes kinetic energy, which is related to the electron's motion. The total energy is essentially the sum of these two components, giving us a complete picture of the electron's energetic state within the atom. Now, when we look at the angular component of the wave function, it depends on the direction or the orientation of the electron relative to the nucleus. This means that the shape of the orbital changes based on where the electron is located around the nucleus in space. On the other hand, the radial component depends on the distance from the nucleus. So, it tells us how the wave function behaves as we move farther away or closer to the nucleus itself. Together, these two components allow us to write the overall wave function, often denoted as psi-n, as a combination of the angular and radial parts. This separation really helps us understand the shape and size of orbitals in a more detailed way. By understanding these components, we're gaining insight into the fundamental nature of how electrons are distributed around the nucleus, which ties back to the overall theme of potential energy and orbital structure in atoms. An orbital in quantum mechanical terms is actually a region of space rather than a specific point. This means that instead of thinking about electrons occupying fixed spots, we think of them as existing within these regions where there's a high probability of finding them. Each solution to the wave equation is labeled with a letter and number combination, like 1s, 2s, 2p, 3s, 3p, 3d, and so on. These labels help us identify different types of orbitals, and each solution defines a particular orbital shape and energy level. Now, the wave function itself, which we denote as psi, has a square, psi squared, that always comes out positive. This squared value actually tells us the probability of finding an electron at any specific point in space. It's important to remember that the wave function can have positive and negative regions, but when we look at its square, those signs don't matter because we're only interested in the probability, which is always positive. So, in essence, orbitals are regions where electrons are likely to be found. Solutions to the wave equations define these orbitals, and the squared wave function gives us a way to visualize the probability distribution of electrons within those regions. Let's start with the idea of a vibrating string fixed at both ends. This simple system actually provides a great way to visualize the solutions to the wave equation. When the string vibrates, it creates specific patterns, or modes, that correspond to different frequencies. These modes are solutions to the wave equation, which describes how waves behave in such systems. Now, shifting gears a bit, in atomic physics, we use something called quantum numbers to name and describe atomic orbitals. These quantum numbers essentially label the solutions we find when solving the wave equation for electrons in an atom. So the key point here is that, both in the case of a vibrating string and in atomic structures, solving the wave equation gives us specific functions or solutions. And these solutions are characterized by quantum numbers, which help us understand and categorize the different possible states. In essence, whether we're looking at strings or atoms, the wave equation and its solutions form the foundation for understanding wave behavior across different physical systems. Let's take a closer look at the quantum numbers involved in solving the Schrödinger equation. First, we have the magnetic quantum number, denoted as. This number specifies the orientation of an orbital within a subshell, giving us insight into the spatial distribution of electrons. Next, there's the secondary quantum number, L, which indicates the shape of the orbital, whether it's spherical, like an s orbital, or more complex, like p, d, or f orbitals. Then, we have the principal quantum number, N, which tells us the energy level or shell that the electron occupies. It can be any positive integer starting from 1 and increasing upwards. These three quantum numbers, N, L, and are fundamental because they collectively describe the unique state of an electron in an atom. Understanding how they work together helps us visualize atomic structure and electron behavior more accurately, which is at the core of quantum mechanics. Each shell in an atom has different energies, which means electrons in different shells will have different levels of energy. When we talk about shells, we denote them with the principal quantum number, N for example, N equals 1 for the first shell, N equals 2 for the second shell, and so on. It's important to remember that N must always be a positive integer, so N equals 1, 2, 3, and so forth. The principal quantum number, N, essentially tells us which shell an electron is in. It helps us understand where an electron is likely to be found around the nucleus. By knowing N, we get a sense of the energy level of the electron's orbital, which is fundamental to understanding atomic structure and behavior. This concept ties into the overall theme of quantum numbers, which describe various properties of electrons within atoms. Now, let's talk about how the shells and subshells are organized. Each shell contains as many L values as its principal quantum number, and so, if N is 3, for example, then L can be 0, 1, or 2. The L value actually specifies the subshell within that shell. Think of it as a way to categorize the different orbitals. The secondary quantum number, L, has integral values starting from 0 up to n-1. This means that as n increases, the number of possible L values also increases, allowing for more subshells within each shell. Essentially, the L value helps us distinguish energy differences among orbitals that are in the same shell, which is crucial for understanding how electrons are arranged and how they behave within an atom. So, in summary, L is key to identifying the subshells and understanding the energy variations among orbitals in the same shell. Now, a third quantum number describes this splitting. When we place atoms in magnetic fields, some of their emission lines don't just stay single, they split into multiple components. In fact, you might see lines splitting into 3, 5, or even 7 parts. This splitting pattern is directly related to the quantum numbers that define the orbitals. Specifically, the energies of these orbitals are fully specified using just 2 quantum numbers: the principal quantum number, N, and the azimuthal quantum number, L. These 2 numbers tell us a lot about the size and shape of the orbitals, and together they help us understand the energy levels and how they behave under external influences like magnetic fields. So, understanding these quantum numbers and their role is key to explaining spectral lines and their splitting patterns. Let's talk about the magnetic quantum number, ML. For the case when L equals 1, can take on the values of -1, 0, and +1. It's important to remember that the absolute value of ML must always be less than or equal to L, so In this case, the values -1, 0, and +1 are all valid because their absolute values are 1 or 0, which are not greater than L also. Can be either positive or negative, reflecting the different orientations of the orbital's magnetic field. And finally, note that has to be an integer value, which means no fractions or decimals. These points are crucial because they help define the possible orientations of an electron's orbital in space, linking directly to how atoms behave in magnetic fields. Let's take a moment to note the relationship between the number of orbitals within the different types, S, P, D, and F, and their magnetic quantum number, ML. As you know, each type of orbital has a specific number of orientations or values for ML. For S orbitals, there is only one orbital with equal to 0. Moving to P orbitals, there are 3 possible ML values, -1, 0, and +1, which means 3 orbitals. For D orbitals, the ML values range from -2 to +2, giving us 5 orbitals. And finally, for F orbitals, values go from -3 to +3, totaling 7 orbitals. This relationship is key because it shows how the number of orbitals within each subshell corresponds directly to the possible orientations in space, as indicated by. Understanding this helps us visualize how electrons are distributed around the nucleus in different energy levels and shapes. It's a fundamental concept that ties together the quantum numbers and the geometry of atomic orbitals, which is essential when we consider electron configurations and chemical bonding. So, each electron has its own axis of spin, which means it possesses angular momentum. These electrons can have 2 distinct orientations or spins, which are labeled as +12 and -12. You can think of these as 2 arrows pointing up and down, respectively, to visually represent their opposite spins. This concept of spin was quite a breakthrough because it introduced a new quantum number called the electron spin quantum number, or. Now, with this addition, we see that the 3 quantum numbers, N, L, and ML, that already describe an atomic orbital can also be used to define its energy, shape, and orientation comprehensively. The electron spin quantum number completes the picture by explaining the intrinsic angular momentum of the electron itself. This is an important step because it helps us understand not just where electrons are likely to be, but also how they behave in terms of their intrinsic properties. It connects to the overall theme of quantum mechanics by showing how quantum numbers give us a detailed, multidimensional picture of atomic structure. Let's take a closer look at some of the key quantum numbers that describe electrons and atoms. First, the refers to the orientation of the electron's spin. Think of it as the electron's own little magnetic orientation, either up or down. Next, we have ML, which designates the orientation of the electron within its orbital. For a given value of L, which tells us the type of orbital, ML can have 2L + 1 different values. This means the number of orbitals in a subshell corresponds directly to the number of possible orientations they can have. Now moving on to the broader picture, in each shell, labeled by the principal quantum number N, there are multiple subshells. The value of L identifies these subshells and also influences the shape of the orbitals, like S, P, or D shapes. For each of these subshells, the number of orbitals is 2L + 1. So, for example, there's 1 S orbital when L equals 0, 3 P orbitals when L equals 1, and 5 D orbitals when L equals 2. Additionally, the L value also affects the energy of the orbital, especially in multi-electron atoms, where energy levels aren't just determined by N, but also by the shape and orientation of the orbitals. Speaking of N, this quantum number defines the shell and essentially sets the size of the orbital. It also has a significant role in determining the energy of the orbital, especially as we move to higher shells. So to sum it all up, these quantum numbers, N, L, ML, and MS, are fundamental because they give us a detailed picture of where an electron is likely to be found, how it behaves, and how it interacts within the atom. They are the building blocks for understanding atomic structure and chemical behavior. Since the lobes are considered along the X, Y, and Z axes, they are designated as shown on the slide. It's important to understand that there is no relation between the first magnetic quantum number and the X, Y, z directions. When we look at boundary surface diagrams, remember that the nucleus is taken to be at the origin. Unlike the spherical shape of the s orbital, the p orbital diagrams are not spherical. Instead, a p orbital consists of two sections called lobes, which are on either side of a plane where the lobes touch each other. Interestingly, the size, shape, and energy of the three orbitals are identical. Boundary surface diagrams are quite useful because they give a good visual representation of the shapes of the orbitals based on constant probability density. These diagrams show surfaces in space where the probability density remains the same. Moving on to the concept of nodes. For an ns orbital, the number of nodes is always one less than the principal quantum number n, so a 2's orbital has one node, and a 3's orbital has two nodes. These nodes are regions where the probability of finding an electron drops to 0, which we call nodal surfaces or just nodes. Now let's talk about how the probability density behaves. For a 2's orbital, the density drops sharply to 0 at a certain point. Then it starts increasing again, reaching a small maximum before decreasing once more and approaching 0 as the distance from the nucleus increases. In contrast, for the 1's orbital, the probability density is highest right at the nucleus and then decreases rapidly as we move away. And remember, according to Max Born, the square of the wave function at any point gives us the probability density of finding the electron there. So, understanding these shapes and densities helps us visualize the behavior of electrons within atoms, tying back into the overall theme of atomic structure and quantum mechanics. Now, let's move on to slide 59, which focuses on boundary surface diagrams for 2p orbitals. These diagrams are a powerful way to visualize the shape and orientation of orbitals in three-dimensional space. They help us understand how electrons are distributed around the nucleus and how these regions of electron density are shaped. In these diagrams, the boundary surfaces represent the regions where the probability of finding an electron is high. They are particularly useful because they give us a clear picture of the lobes, which in the case of 2p orbitals are oriented along specific axes, x, y, and this orientation is crucial because it influences how atoms bond and interact with each other. What's important to grasp here is that these boundary surface diagrams not only show us the shape, but also help us understand the directional properties of the orbitals. For example, the TP-X orbital has a lobed shape along the x-axis, while the TP orients along the y-axis and TP-Z along the z-axis. By visualizing these orbitals, we gain deeper insight into how atomic orbitals contribute to molecular geometry and bonding patterns. This understanding is fundamental as we explore how atoms combine to form molecules and how the shape and orientation of orbitals influence chemical behavior. When two nodal planes pass through the same origin and bisect both the xy plane and the z plane, we call these angular nodes. These are important because they describe the regions where the probability of finding an electron is 0, and they help define the shape of the orbital. Moving on to the d orbitals, for orbitals where the principal quantum number n is greater than 3, their shapes resemble that of the 3d orbital, but they differ in energy. This means that as we go to higher energy levels, the d orbitals maintain similar shapes but are shifted in energy, which influences their chemical behavior. Now, when we look at the first 4d orbitals, you'll notice their shapes are quite similar to each other. However, the fifth d orbital has a different shape from the others. Despite this difference, all 5d orbitals are part of the same set and are degenerate, meaning they all have the same energy in a given atom. Finally, these 5d orbitals are collectively designated as the d orbitals. Understanding their shapes, energy levels, and how they relate to each other is fundamental to grasping the complexities of electron configurations and chemical bonding in transition metals. As we've seen, the 2p and 2s orbitals are different types of orbitals, but interestingly, an electron has the same energy whether it's in the 2p or the 2s orbital. This is because they are degenerate, meaning their energies are equal despite their different shapes and orientations. Now, regarding the energies of orbitals, the order in which they increase is quite important. It goes like this. The 1's orbital has the lowest energy, then the 2's and 2p orbitals are higher, and these are equal in energy. Next come the 3's, 3p and 3d orbitals, which are higher still, and finally the 4's, 4p, 4d, and 4f orbitals. This sequence helps us understand how electrons fill atoms in order of increasing energy. Let's also talk about nodes in these orbitals. The total number of nodes an orbital has is given by the formula n1. This total includes both radial nodes, which are spherical, and angular nodes, which are planar or conical. The sum of these nodes equals n1. Specifically, the angular nodes are related to the shape of the orbital, and their number is denoted by L. For example, p orbitals have one angular node, which gives them their characteristic dumbbell shape, while d orbitals have two angular nodes, giving them more complex shapes. To summarize, angular nodes are a key concept in understanding orbital shapes and are directly related to the quantum number L. Recognizing the number of angular nodes helps us visualize how electrons are distributed in space around the nucleus. Let's start by looking at how the attractive interactions of an electron change with the positive charge on the nucleus. As the positive charge, represented by Z, increases, the electrostatic attraction between the nucleus and the electron also increases. This means the electron is held more tightly as the nucleus becomes more positively charged. Next, consider the electrons in a hydrogen atom. When electrons occupy the 2's, 2p, or higher energy orbitals, they are said to be in an excited state. This is a higher energy condition compared to when they are in the lowest possible energy state. Now, talking about energy levels, orbitals that have the same energy are called degenerate orbitals. In a hydrogen atom, the 1's orbital is the most stable, meaning it has the lowest energy. This is known as the ground state. An electron residing in this 1's orbital is strongly attracted and held tightly by the nucleus, which explains why this state is the most stable. So, understanding these concepts helps us grasp how electrons behave and how their energy states influence the stability and interactions within an atom. So, in essence, what we're looking at is how the energy of interaction between the nucleus and the electron changes as the atomic number, Z, increases. And what we see is that this energy actually decreases with a higher Z. The reason behind this is related to what we call shielding. Inner shell electrons partially block or screen the positive charge of the nucleus from the outer electrons. This phenomenon is known as shielding of outer electrons by inner shell electrons. Because of this shielding effect, the outer electrons don't feel the full positive charge of the nucleus. This leads us to the concept of the effective nuclear charge, which is essentially the net positive charge experienced by outer electrons after accounting for the shielding effect. So, even though the nucleus has a certain positive charge, the inner electrons reduce the pull felt by the outer electrons. As a result, the presence of electrons in the inner shells means that the outer shell electrons are not experiencing the full attraction of the nucleus. This is a key concept to understand when we're talking about atomic structure and how electrons are arranged and behave across different elements. Let's take a closer look at the order of increasing energy in atomic orbitals. The sequence, starting from the lowest energy, goes like this. 1's, 2's, 2p, 3's, 3p, 4's, 3d, 4p, 5's, 4d, 5p, 4f, 5d, 6p, 7's, and so on. This order is crucial because electrons fill the orbitals starting from the lowest energy level, and only once those are filled do they move on to higher energy orbitals. This concept is at the heart of the Aufbau principle, which explains how electrons are arranged in the ground state of atoms. Essentially, electrons will always occupy the lowest available energy orbitals first, following this specific order. This principle helps us understand the electronic configuration of elements and why they behave the way they do chemically. So, in summary, electrons fill orbitals in a specific sequence dictated by their energy levels, and the Aufbau principle formalizes this process, ensuring we can predict atomic structures accurately. This understanding connects directly to our overall theme of atomic behavior and chemical properties. The maximum number of electrons that can fit in a shell with a given quantum number n is determined by the 2n2 rule. This means that as n increases, the capacity of the shell increases exponentially. It's a fundamental principle that helps us understand how electrons are arranged in atoms. Additionally, it's important to note that only 2 electrons can occupy the same orbital, and these electrons must have opposite spins. This is crucial because it prevents electrons from being in the same quantum state. According to this principle, no 2 electrons in an atom can share the same set of 4 quantum numbers. This restriction is what we call the Pauli exclusion principle, and it's key to understanding the structure of atoms and how electrons fill available orbitals. It ties into our overall theme of how quantum mechanics governs atomic structure, shaping the way electrons are distributed and how atoms behave. Some of the orbitals acquire extra stability due to their symmetry, which is quite interesting because it affects how electrons are arranged. Now, this slide states that pairing of electrons in the orbitals belonging to the same subshell, such as p, d, or f, does not happen immediately. Instead, electrons will first singly occupy each orbital within that subshell. This means that before any pairing occurs, each orbital gets 1 electron, following a specific order. This rule is particularly important when we're looking at the filling of electrons in degenerate orbitals. That is, orbitals within the same subshell that have the same energy. So, in essence, Hund's rule guides us to fill these orbitals in a way that maximizes the number of unpaired electrons with parallel spins, leading to more stability. By understanding this rule, we can predict the electron configuration more accurately and appreciate how the symmetry and energy considerations influence the overall stability of atoms. This ties into the broader theme of electron configurations and how atomic structure determines chemical properties. Now, let's wrap up with a key concept about electrons in atoms. The electrons in the completely filled electronic shell with the highest principal quantum number are called valence electrons. These are the electrons that are most involved in chemical bonding and reactions. As mentioned earlier in the textbook, understanding valence electrons helps us predict how elements will interact. Moving on, we see there are different ways to represent an atom's electronic structure. One way is the normal notation, which is a straightforward way to show the electron distribution. The other is the orbital diagram, which visually illustrates how electrons occupy specific orbitals. Remember, the distribution of electrons into the orbitals of an atom is what we call its electronic configuration. This configuration is fundamental because it determines the atom's chemical properties and behavior. So, in summary, electronic configuration gives us a detailed map of where electrons are in an atom, and knowing the valence electrons helps us understand chemical bonding. These concepts are essential for grasping the overall theme of atomic structure and reactivity.